It is a curious thing that the most enduring monument on Earth may also be the most quietly precise. Stand at the base of the Great Pyramid of Giza, and you see only mass, 6 million tons of limestone rising from the desert in solemn defiance of time. But beneath that weight lies something far more unsettling than stone: precision. Measured in modern surveys, the base of the Great Pyramid extends roughly 230.3 meters on each side. The variation between its longest and shortest sides is less than 5 centimeters. Across a distance longer than 2 football fields, the deviation is smaller than the width of a human hand. Its foundation is level to within approximately 2.1 centimeters, over 13 acres of stone. Pause for a moment and consider what that means. This structure was completed around 2560 BCE. The conventional tools attributed to its builders include copper chisels, dolerite pounding stones, wooden sledges, rope, plumb bobs, and sighting rods. No steel, no precision optics, no laser leveling, no theodolites, no modern survey grids. And yet, the base sits so flat that modern engineers still remark upon it with a certain quiet discomfort. Here is the measurable engineering fact that refuses to sit politely within our assumptions. The Great Pyramid's dimensional accuracy and leveling precision exceed what we would normally expect from a society working with the tools traditionally attributed to Old Kingdom Egypt. Not impossibly so, but uncomfortably so. That is where our journey begins. For this is not a story of aliens, nor of hidden knowledge whispered by forgotten gods. It is a story about something far more grounded, and therefore far more intriguing: measurement. Because when we examine the pyramid not as myth, but as mathematics, a deeper pattern begins to emerge. Its dimensions are not arbitrary. They are expressed in a unit known as the royal cubit. The royal cubit measures approximately 52.3 centimeters. Archaeologists have recovered physical cubit rods from ancient Egypt, carefully marked, subdivided into palms and digits, inscribed with astonishing clarity. These were not rough estimates based on a forearm. They were standardized instruments. One such rod, dating to the reign of Pharaoh Amenhotep III, shows subdivisions to within millimeter consistency. Multiple rods, discovered in different periods, reveal striking uniformity, which raises the first quiet tension in our narrative. Standardization implies oversight. Oversight implies institutional knowledge. Institutional knowledge implies a system, one capable of maintaining consistency across generations. But Egypt was not alone. In Mesopotamia, measuring rods have also been unearthed, carved, calibrated, subdivided. The Sumerians and Babylonians employed cubits of their own, distinct in value yet structured in similar hierarchical divisions. In the Indus Valley, ivory rulers marked with precise intervals suggest a comparable devotion to standardized measurement. Different cultures, different languages, different gods. And yet, a recurring pattern emerges. A base unit derived from the human body, formalized into a rigid standard, subdivided with mathematical consistency and applied to monumental architecture. Now consider the implications. To construct a building the size of the Great Pyramid, composed of an estimated 2.3 million stone blocks, requires not merely brute force, but repeatability. Each course must maintain consistent height, each corner must align, each edge must preserve angle. If the cubit varied from team to team, from season to season, from quarry to construction site, the structure would drift, errors would compound, corners would misalign, but they did not. The pyramid's orientation is aligned to true north within approximately 0.05 degrees. Modern analyses suggest this was achieved using stellar observations, perhaps sighting circumpolar stars. But even stellar alignment requires stable baselines and precise angular measurement. A rope can sag, wood can warp, copper dulls, and yet the final structure remains, not merely massive, but mathematically coherent. Here is the deeper question. one we will return to again and again on this journey. What underlying measurement system could produce this level of architectural precision without advanced instruments? Not magic, not myth, but method. If we assume the builders possessed only rudimentary tools, then their results imply a mastery of calibration, repetition, and error correction that rivals early modern engineering, which forces us to confront a subtle possibility. Perhaps we have underestimated not their strength, but their systems. Because the Great Pyramid is not a chaotic monument, it is ordered. Its height originally measured approximately 280 royal cubits. Each side of its base measures 440 royal cubits. These are not random values. They are integers within a standardized system. Even more compelling, the slope of the pyramid is defined by a ratio known in Egyptian mathematics as the secked, which expresses horizontal run per vertical rise. It is a practical geometric method, elegant in its simplicity, yet capable of producing astonishing consistency. We often imagine ancient builders as improvisers, adjusting by eye, correcting by instinct. But the data suggests something else. They were system builders, and systems can travel. When we compare measurement practices across early civilizations, we find recurring structural themes. Base units anchored in human proportions, subdivided in regular fractions, institutionalized through physical rods, applied to architecture with repeatable discipline. The question is not whether ancient cultures influenced one another. Trade networks certainly existed. The question is more technical. Were these measurement systems convergent solutions to universal engineering constraints? Or do they point to a deeper shared baseline, a foundational logic of construction that spread farther and earlier than we currently model? For now, let us remain with the pyramid. Imagine standing on that foundation as it was first laid, a vast square carved into bedrock, leveled with channels possibly filled with water to determine flatness. Imagine teams checking cubit rods against master standards. Imagine overseers verifying angles by star positions, ropes stretched taut across open desert, recalibrated again and again. This is not mysticism, it is quality control. And quality control in 2560 BCE is a far more radical concept than most realize. If you are finding yourself unsettled, intrigued by this quiet precision, then stay with me. Subscribe, if you will, not out of habit, but out of genuine curiosity. Because this journey will demand patience, and it will reward it. For we have only just uncovered the first layer of this stone enigma. The Great Pyramid stands as a silent equation. Its dimensions resolve cleanly within a standardized unit. Its leveling challenges expectation. Its orientation flirts with astronomical accuracy. Its scale magnifies even the smallest error, yet the errors remain astonishingly small. And it is not alone in history. So we must ask, if multiple ancient civilizations formalized and standardized measurement to a degree that enabled monumental precision, what does that imply about their technological sophistication? Have we misjudged the capabilities of the ancient world, not because of lost machines, but because of lost respect for disciplined systems? The desert remains silent. The stones offer no confession, but the numbers whisper. And in those numbers lies a tension that refuses to fade. What underlying measurement system, shared, calibrated, enforced, could produce such precision long before the age of steel and glass? That is the mystery we now step toward, and it grows deeper with every measured stone, and so we follow the numbers backward. Before the pyramid was stone, it was measurement. Before measurement was rod, it was body. The cubit begins, as many ancient units did, in flesh and bone, the length from elbow to fingertip. A practical choice, always available, universally human. In a world without factories or digital calibration, the body was the first instrument, but the body is inconsistent. No two forearms are identical. Even within a single population, variation can span several centimeters. If a mason measured blocks with his own arm and another with his, the structure would drift almost immediately. A wall built over years would swell and contract unpredictably. Precision would dissolve into approximation. Yet that is not what we see in Egypt. Instead, we find something far more deliberate. The Egyptian royal cubit, used in pyramid construction, measures approximately 52.3 centimeters. Not about, not roughly. Archaeological finds of cubit rods, carved from stone or wood, confirm a remarkable consistency across centuries. They are subdivided into 7 palms, each palm divided into 4 digits. 28 digits to a cubit, a clean, rational system. One rod discovered in the tomb of the architect Ka, dating to the 18th dynasty, displays divisions marked with extraordinary care. Another, from the reign of Amenhotep III, shows near-identical calibration. The deviations between surviving rods are minimal, often within millimeters. This is no longer anatomy. This is standardization. Some rods even bear inscriptions warning against tampering, suggesting that these were official references, master standards against which working tools were checked. The implication is subtle but profound. Egypt maintained a controlled measurement system, and that shifts the narrative. We often imagine ancient standardization as crude or regional, evolving slowly through trial and error. But the evidence suggests something more organized, a bureaucracy of measurement. In Mesopotamia too, measuring rods have been recovered. The Sumerians used a cubit of roughly 49 to 50 centimeters, subdivided into fingers and hands, embedded within their base 60 mathematical system. Clay tablets from Babylon record conversions between units with algorithmic clarity. Measurement was not casual, it was codified. Even more striking, the Indus Valley civilization produced ivory rulers marked with subdivisions that imply extraordinary precision, some divisions spaced to within less than 2 millimeters of uniformity. These artifacts predate 2000 BCE. Different cultures, different political systems, yet all converging on a similar solution: the body-derived unit formalized into an invariant standard. The transition from body to rod is not trivial. It requires agreement. Agreement requires authority. Authority requires enforcement. A master cubit must be preserved somewhere, perhaps in a temple, perhaps under priestly control, perhaps guarded as part of state infrastructure. Working rods would need periodic comparison. Damaged rods would need replacement. Builders would require training in subdivisions. In other words, measurement became institutional. And once institutional, it became scalable. Consider what this means for the Great Pyramid. If its base measures 440 royal cubits per side, that figure implies not approximation, but intent. The design was conceived in cubits, not meters. The architects thought in units that were internally consistent. Millions of stones were cut, transported, and set according to a shared reference. If even one work crew operated with a rod off by half a centimeter, the cumulative deviation across 440 cubits would exceed 2 meters. The pyramid would not close cleanly at the apex. Angles would distort, courses would misalign, yet the structure resolves, which forces us to reconsider an assumption. We tend to believe that ancient societies were technologically limited because their tools were simple. Copper is soft, wood bends, rope stretches, therefore precision must have been limited. But the cubit rod suggests another truth. Precision does not begin with the tool, it begins with calibration. A wooden rod, if checked against a master standard regularly, can maintain consistency. A rope, if tensioned and corrected repeatedly, can serve as a surprisingly accurate linear measure. A plumb bob, governed by gravity, is indifferent to the century in which it hangs. Perhaps we have underestimated not their materials but their discipline, and discipline is measurable. The consistency of cubit rods across different periods in Egypt implies long-term preservation of a reference length. The same basic royal cubit persists for centuries with only minimal drift. That continuity demands record-keeping, replication methods, and controlled transmission. This is not an isolated invention. Measurement systems in Mesopotamia show similar durability. Clay tablets describe land plots, canal dimensions, temple layouts, all expressed in standardized units. Errors in land measurement would have legal consequences. Standardization was not aesthetic, it was economic, which raises a deeper tension in our narrative. If multiple civilizations independently formalized anthropic units into highly stable standards at roughly similar periods in antiquity, does this reflect simple convergence? Or does it suggest something more coordinated, whether through trade networks, shared intellectual exchange, or parallel administrative evolution? We must tread carefully here. There is no evidence of a secret global authority of measurement, no hidden council distributing rods across continents, but there is evidence of contact between regions. Trade routes connected Mesopotamia and the Indus. Egypt traded with the Near East. Goods moved. Ideas likely moved with them. Measurement, after all, is fundamental to commerce, and commerce demands agreement. Imagine a caravan arriving with timber, copper or grain. Quantities must be verified, contracts must be honored. If two regions operate on wildly different units, trade slows. But if base units are convertible, if cubits resemble cubits, exchange becomes smoother. Over time, practical compatibility could produce remarkable similarity, and yet the Great Pyramid stands apart in scale. Standardization in trade is one thing. Standardization across 13 acres of leveled bedrock is another entirely. To lay a foundation so flat, workers may have carved channels into the bedrock and filled
them with water to determine a level plane, a primitive but effective technique. But such a method still requires consistent linear measurement to ensure square corners and equal sides. And here we encounter the tension that drives our investigation. The cubit began as the human forearm, variable, organic, imprecise. Within centuries it became a fixed rod, subdivided into rational fractions, replicated across institutions, applied to architecture with astonishing consistency. The transformation from flesh to standard was not accidental. It was engineered. If you are still with me, if the quiet story of rods and ratios has begun to feel unexpectedly profound, then consider subscribing, because what we are uncovering is not merely history, it is the architecture of order itself. Measurement is civilization's invisible skeleton. Without it, monuments cannot rise. With it, even copper tools can produce enduring geometry. But one question now presses forward, heavier than before. The cubit was standardized, the rods were consistent, the subdivisions were rational. Yet how, in practice, did builders maintain centimeter-scale consistency across decades of labor, across thousands of workers, across quarries and construction ramps, under the shifting heat of the Egyptian sun? A master rod in a temple is one thing. 2 million stones aligned within millimeters is another. How did they ensure that the system did not drift? How did they prevent the smallest deviation from multiplying into visible failure? Because in structures of such magnitude, error is relentless, and yet somehow it was restrained. That is where our journey now turns, from the rod to the rope, from the unit to the baseline, from the concept of standardization to the art of enforcing it at monumental scale. And there, in the dust between stretched cords and rising stone, lies the next piece of this measured mystery. And so we arrive at the rope drawn tight across sand. Before a single stone was lifted, before ramps were raised or blocks quarried, there was a line. Invisible now. Long erased by wind. But once stretched across the Giza plateau with deliberate intent, a baseline from which everything else would follow. Surveying is the quiet foundation of architecture. Without a straight reference line, there can be no square. Without a square, no pyramid can rise true. Today, we rely on theodolites, laser levels, total stations capable of measuring angles to fractions of a second. But in the 4th dynasty of Egypt, none of these existed. No optics, no magnified sight lines, no digital corrections for curvature or refraction. And yet the Great Pyramid is aligned to true north, with an error of approximately 3 arc minutes, about 1/20th of a single degree. Let that settle. 3 arc minutes. Modern surveys, beginning with Sir Flinders Petrie in the 1880s and refined by contemporary total station measurements, consistently confirm this astonishing alignment. Petrie's careful triangulations revealed deviations so small they initially seemed improbable. Later studies using modern instrumentation corroborated his findings. The sides of the pyramid are not merely roughly north-south, they are almost precisely cardinal. This is not aesthetic coincidence, it is measured intent. Now we must confront our core question once more. What measurable engineering fact does not match the assumed technological capability? Here it is in stark form. The Great Pyramid's orientation to true north rivals, and in some cases exceeds, what many medieval European cathedrals achieved with more advanced tools. And Egypt did it 2.5 millennia earlier. How? The prevailing explanation is astronomical. The Egyptians were careful observers of the night sky. Without Polaris marking the pole as it does today, they may have used pairs of circumpolar stars, perhaps Kochab and Mizar, aligning them vertically as they crossed the meridian. By observing the moment when one star lay directly above the other, surveyors could mark a true north-south line. This method is plausible. It requires patience, repetition, and clear skies. But plausibility is not proof. Even if stellar alignment established a north-south axis, translating that axis into a 230-meter baseline introduces new layers of error. A rope stretched across desert terrain will sag. Stakes driven into soil can shift. Heat expands materials. Human sighting introduces parallax. And yet the pyramid's sides remain nearly square. The difference between its longest and shortest sides is measured in centimeters. To appreciate the scale of this achievement, imagine marking out a perfect square whose sides extend longer than 2 modern football fields. Now imagine doing so without steel tapes, without transit, levels without GPS correction. One method often proposed involves the use of a stretching of the cord ceremony depicted in Egyptian reliefs. A pharaoh, assisted by a priest, pulls a rope taut between stakes. Symbolic, certainly, but perhaps also practical. Rope, if braided tightly and pre-tensioned, can be surprisingly consistent in length. If measured against a master cubit repeatedly, corrected for wear, and kept dry, it could serve as a linear instrument. Knots could mark subdivisions. Assistants could maintain tension while alignment was sighted using plumb bobs and simple sighting rods. But again, the scale magnifies every flaw. Suppose a rope 100 meters long stretches by only 1 centimeter due to tension or humidity. Across 2 perpendicular axes, such deviations could distort the square. Multiply this across multiple remeasurements and error accumulates, unless there was a method of correction. One compelling possibility is redundancy. Rather than relying on a single measurement, surveyors may have measured each side multiple times from different reference points. Diagonals could be checked to confirm squareness. If the 2 diagonals of a square are equal, the angles are true. This is not advanced mathematics. It is geometry embedded in practice. The Egyptians understood right angles, the so-called 3-4-5 triangle, a simple integer ratio producing a right angle, may have been used with knotted ropes. Stretch 3 units along one side, 4 along another, and the diagonal must measure 5 if the angle is true. Such techniques are ancient, they are elegant, and they are within reach of Copper Age technology. But here is where the tension sharpens. Even if we grant stellar alignment, even if we grant rope-based geometry, even if we grant repeated correction and redundancy, we must still account for the consistency achieved over a base cut directly into limestone bedrock. Excavations suggest the builders leveled the plateau itself before construction began. Channels carved into the rock may have been filled with water to determine a common horizontal plane. Water seeks its own level. It is nature's own spirit level. This technique is credible. But carving channels across 13 acres, maintaining uniform water height, compensating for evaporation and seepage,
This is labor-intensive precision. It demands organization and oversight. We are no longer discussing primitive improvisation. We are discussing engineered procedure, and here is what unsettles many modern observers. The procedures required to achieve this alignment are conceptually sophisticated, yet mechanically simple. No single step is impossible. But the integration of all steps, astronomical observation, baseline establishment, squaring, leveling, error correction, into a coherent workflow that produces sub-degree precision across massive scale, that is rare in pre-industrial contexts. It suggests something else entirely, not lost technology, not impossible knowledge, but institutional mastery of surveying. A culture in which specialists trained not merely in ritual but in measurement, a system where baseline verification was not optional but mandatory, a construction philosophy that treated orientation as sacred and therefore non-negotiable. Why such devotion to cardinal alignment? Religious symbolism, certainly. The pharaoh's pyramid aligned with cosmic order, with the eternal circumpolar stars. North was not arbitrary, it was metaphysical. But symbolism does not produce precision on its own. Method does. If you are beginning to sense that this story is less about mystery and more about underestimated competence, then remain with me. Subscribe if you wish, not for spectacle, but for clarity. Because clarity, in this case, is more astonishing than myth. We stand now on a wind-swept plateau 4,500 years ago. Night sky overhead, surveyors watching stars wheel slowly around the pole, assistants gripping cords, stakes driven into bedrock, measurements repeated, whispered, checked again. There is no laser beam, there is no optical lens, only eye, rope, rod, water, and relentless correction. And yet the result remains measurable today, with instruments those surveyors could never have imagined. And it holds. 3 arc minutes from true north, centimeter deviations across hundreds of meters. The measurable facts are not in dispute. The tools, as we understand them, are simple. So we are left with a narrowing gap between assumption and evidence. If they lacked modern instruments, how did they achieve such alignment precision? Was it repetition beyond our expectation? Astronomical insight beyond our models? Or a surveying discipline more rigorous than we have allowed ourselves to imagine? The rope is stretched, the stars are fixed, the baseline is drawn, but the method, the full method, still waits to be uncovered. The line has been drawn, the ground has been leveled, the square has been set against the turning of the stars. Now the pyramid begins to rise, not randomly, not approximately, but according to a quiet internal logic, one that reveals itself only when we examine the structure in the units its builders actually used. We often measure the Great Pyramid in meters and degrees, as though the ancient world were thinking in modern terms. But the architects of Giza did not speak in meters. They thought in royal cubits. And when we translate the pyramid back into that language, something remarkable happens. Its original height was 280 royal cubits. Each side of its base was 440 royal cubits, not 438, not 443. Whole numbers, clean numbers, deliberate numbers. This is not the signature of rough estimation. It is the signature of design conceived within a stable measurement system. The ratio between base and height, when expressed in these cubits, produces a slope that has intrigued observers for centuries. Many modern commentators rush to connect this slope to later numerical constants. We will tread carefully there. Because the Egyptians did not describe slopes as we do, they used something called the secked. The secked is not an angle in the modern sense. It is a practical builder's description. It tells you how much horizontal distance the pyramid extends outward for every unit it rises vertically. Imagine you are standing at the center of the pyramid's base. For every cubit the pyramid rises upward, it steps outward by a specific number of palms. That outward measure is the secked. For the Great Pyramid, that outward run is 5.5 palms for each cubit of rise, 5.5, a fraction easily expressed in their system, not abstract, not mystical, simply 5 palms plus 2 digits. This choice produces the slope we see. Now consider what this means in practice. If you are a builder working with cubit rods marked into palms and digits, you do not need advanced theory. You do not need symbolic notation. You simply measure upward 1 cubit, outward 5.5 palms, and continue. The slope emerges naturally, layer upon layer, course upon course. The beauty of this system lies in its practicality. It translates vertical ambition into horizontal measurement without requiring complex instruments. It is embodied geometry, held in the hand. But here is where modern analysis becomes unsettled. When we measure the completed pyramid in meters, the relationship between its perimeter and its height appears to approximate a value that later cultures would associate with the circle. The ratio between half the base and the height appears strikingly close to proportions that have fascinated mathematicians for centuries. Some have claimed this proves advanced knowledge of constants far beyond the documented mathematics of Old Kingdom Egypt. But we must pause. If the pyramid's dimensions are 440 cubits per side and 280 cubits high, those numbers alone define its shape. The secked of 5.5 palms determines the outward spread. The resulting proportion is not mysterious when viewed from within the cubit system. It is an outcome of whole number design, and yet the closeness of certain modern comparisons remains astonishing. Not perfect, but close enough to raise eyebrows. The crucial question becomes this: did the builders intentionally encode those relationships, or are we observing the natural byproduct of a measurement system built on rational subdivisions and whole number planning? The secked system inherently favors tidy fractional relationships. 5.5 palms per cubit is manageable. It can be marked on a rod. It can be checked by eye. It avoids awkward subdivisions. In striving for constructability, the builders may have inadvertently produced proportions that resonate with later numerical ideas. In other words, elegance may arise from practicality, but the deeper intrigue lies not in speculative constants. It lies in consistency. The slope remains uniform across the faces. The courses maintain regularity. The corners meet with astonishing coherence. When modern surveys examine the casing stones that once covered the pyramid, their angles confirm that the intended slope was executed with minimal deviation. This is the measurable fact. Over a vertical rise of nearly 147 meters, the deviation in slope is minute. The structure does not bulge outward unpredictably. It does not taper unevenly. Such uniformity implies more than inspiration. It implies control. Imagine the challenge. Each layer must recede inward at exactly the intended rate. If one course extends too far, the next must compensate. If compensation fails, the error compounds, and yet the pyramid closes. When translated into cubits and palms, the numbers feel almost serene. They resolve into whole relationships. They suggest that the architects were not improvising as they climbed. They were following a template embedded in measurement. It is worth reflecting on how radical this is. In an age without printed plans, without standardized blueprints, without mass-produced measuring tools, the Great Pyramid manifests a geometric clarity that modern observers still debate. Not because it is impossible, but because it is disciplined. And discipline, in this context, is the hidden technology. If you are beginning to sense that the mystery of Giza is not hidden chambers or secret codes, but the relentless consistency of its design logic, then stay with this journey. Subscribe, if you wish, not for spectacle, but for the slow unfolding of understanding. Because what we are uncovering is a civilization fluent in measurement. The secked was not theoretical abstraction, it was construction language. It allowed workers to translate a master plan into physical reality without needing to grasp the full conceptual picture. A foreman could call out the required run for each rise, Teams could check alignment using rods and sight lines. Corrections could be made before deviation became visible. Over time, this method produced a monument whose proportions seem almost preordained. And yet, there remains a tension we cannot ignore. When later cultures rediscovered certain numerical relationships embedded in circles and spirals, they treated them as profound revelations. When modern analysts map those same relationships onto the Great Pyramid, the fit appears tantalizing. But correlation is not intention. We must ask ourselves, are we projecting backward? Is the closeness of these proportions a deliberate act of design, evidence that Egyptian architects grasped deeper numerical truths than surviving records reveal? Or is it coincidence born from a rational building system optimized for stability and simplicity? The secked provides one answer: practical slope control. The whole number cubit dimensions provide another: design within a stable unit framework. But the overlap between ancient practicality and later numerical fascination remains provocative. The pyramid stands silent, its stones offering no commentary, yet its geometry continues to whisper. Are these ratios intentional? Or are we witnessing the beautiful coincidence that arises when disciplined measurement meets monumental ambition? The next step in our journey will press this question further, beyond Giza, beyond Egypt, into patterns that echo across civilizations. And there, the coincidence begins to feel less accidental. Subscribe to our channel if you love the content. The pyramid does not speak, but numbers invite interpretation. For generations, observers have stood before the Great Pyramid and noticed something that feels almost too elegant to ignore. If one takes the perimeter of its base and compares it to twice its original height, the proportion comes strikingly close to a value that later civilizations would associate with the circle. The comparison is not exact, but it is close enough to stir the imagination. And here, imagination has often outrun evidence. Some have claimed this closeness proves that the pyramid's architects possessed advanced knowledge of constants far beyond what surviving Egyptian texts reveal. Others suggest hidden wisdom encoded deliberately into stone. But when we slow down, when we step back into the mindset of Old Kingdom builders, a different explanation emerges. One that is less sensational, but far more revealing. To understand it, we must return to the secked. As we saw, the slope of the Great Pyramid is defined not by abstract angles, but by a practical instruction. For every cubit the structure rises, it extends outward by 5.5 palms. That simple design choice, 5.5 palms per cubit, determines everything that follows. From that instruction, the full height of 280 cubits and the base of 440 cubits per side are not arbitrary. They are consistent, logical, executable within the cubit system. And when you build a pyramid with those dimensions, something interesting happens. The proportions align in such a way that modern measurements produce a value remarkably close to what we now recognize in the geometry of circles. But the key word here is produce. The proportion emerges from the design system. It is not necessarily the guiding principle behind it. The archaeological consensus is cautious. We possess Egyptian mathematical texts, most notably the Rhind mathematical papyrus, which demonstrate that Egyptian scribes understood practical geometry. They could calculate areas. They could approximate circular shapes for agricultural and architectural purposes. But there is no surviving evidence that Old Kingdom architects possessed a theoretical concept of circle constants as formalized later in Greek mathematics. What they did possess was a consistent fractional system and a deep familiarity with practical ratios. When working within whole cubits and rational subdivisions, certain proportions will inevitably produce shapes that modern observers find numerically intriguing. But intriguing does not mean intentional. It is important to recognize how easily retrospective analysis can impose meaning. When we measure the pyramid in meters, convert those measurements into modern decimal systems, and then compare them to later constants, We are layering interpretive frameworks onto a structure conceived in a completely different numerical language. The Egyptian builders did not think in decimals, they thought in unit fractions. They did not describe slopes as abstract angles, they described them as horizontal run per vertical rise. 5.5 palms per cubit, that is the key. Choose that slope, perhaps for structural stability, perhaps for aesthetic reasons, perhaps for symbolic harmony, and the resulting proportions follow naturally. If one alters the secked slightly, the relationship shifts. A slope of 5 palms per cubit would produce a noticeably steeper pyramid. 6 palms would yield something shallower. 5.5 sits in a practical middle, stable, constructible, visually imposing. It is possible, even likely, that the choice was guided by practical considerations: load distribution, ease of stone placement, stability of casing blocks. The fact that this practical slope produces a modern numerical resemblance to later circle relationships may be an elegant accident, yet here is where the tension lingers. The closeness is not vague. It is precise enough that many engineers and mathematicians have paused. The difference between the pyramid's proportion and the later mathematical value is small, smaller than one might expect from rough construction. But it is not perfect, and that imperfection is telling. If the builders had been deliberately encoding a theoretical constant, we might expect a cleaner match. Instead, what we see is the natural outcome of whole number design constrained by the cubit system. In other words, the pyramid behaves like a structure built by disciplined engineers, not like a coded manuscript. This distinction matters because it reframes the mystery. If the proportion is not evidence of hidden advanced mathematics, then what is it evidence of? It is evidence of internal coherence. It shows that the builders worked within a consistent measurement framework. It shows that their slope system, expressed through the secked, was capable of producing grand architectural harmony without requiring abstract theoretical knowledge. It shows that elegance can arise from practicality. But there remains a subtle unease, for even if we accept that the resemblance to later constants is incidental, we are still left with a monument whose dimensions resolve with extraordinary precision inside its own measurement system. The base is an even 440 cubits, the height an even 280, the slope a clean fractional instruction, the casing stones aligned to maintain uniformity. Nothing about this is casual. If you are enjoying this journey into the discipline beneath the desert, then stay with it. Subscribe not for sensational claims, but for the slow excavation of fact from fascination. Because what we are uncovering is more compelling than myth. The Great Pyramid does not need secret knowledge to be extraordinary. Its achievement lies in system integrity. And yet, we must not dismiss curiosity too quickly. Even if the proportion approximating later circle geometry is a byproduct of the secked system, we must still ask why the secked was chosen as it was. Why 5.5 palms per cubit? Why not 5? Why not 6? Was the choice purely structural? Was it aesthetic? Was it inherited from earlier pyramid experiments and refined through trial? The archaeological record shows that earlier pyramids did experiment with different slopes. The bent pyramid, for example, shifts its angle mid-construction, perhaps due to structural concerns. The Great Pyramid appears to represent a culmination, a refinement, which suggests intention, but intention within engineering limits. So we stand at a careful boundary. On one side, overinterpretation, the temptation to project later mathematical knowledge backward into deep antiquity. On the other side, underestimation, the tendency to dismiss ancient engineers as merely practical laborers, without abstract thought. The truth likely lies between. They were practical, they were disciplined, they understood proportion deeply within their own framework. And that framework, when translated into our modern system, produces results that feel almost prophetic. But prophecy is a dangerous lens. The real mystery is not whether the pyramid encodes advanced constants. The real mystery is this: if the resemblance is unintentional, if it emerges naturally from the secked system and whole number cubit planning, why does that system produce such remarkably precise outcomes at monumental scale? Why do the numbers align so cleanly? Is it coincidence born of rational design? Or does it hint at a deeper architectural philosophy, one we have yet to fully reconstruct? The stones do not answer, they only hold their proportions, and the proportions continue to provoke. Before we continue the journey, share your thoughts in the comments section. The pyramid stands in Egypt, but measurement does not belong to Egypt alone. If the story ended at Giza, we might be tempted to treat its precision as an isolated flowering, a local triumph of discipline in a singular river valley. Yet when we widen the lens, when we step beyond the Nile and move eastward across the Fertile Crescent, then further toward the Indus, something unexpected emerges. Rods, standards, subdivided lengths carved into durable material. In Mesopotamia, among the Sumerians and later the Babylonians, archaeologists have uncovered measuring bars marked with consistent intervals. Clay tablets record land divisions, canal widths, temple foundations. Their base unit, often translated as a cubit, varied slightly in length from the Egyptian royal cubit, but the structure of the system feels familiar. A primary unit derived from the body, subdivided into smaller fractions, embedded within administrative and architectural practice. In some cases, these Mesopotamian rods appear calibrated with a precision that implies replication from a master reference. They were not casual sticks cut to approximate size. They were instruments of governance. Land disputes depended on them, taxation depended on them, construction depended on them. Further east, in the cities of the Indus Valley, Harappa, Mohenjo-Daro, archaeologists have uncovered ivory rulers marked with evenly spaced graduations. The spacing is so consistent that modern measurement reveals only minimal variation across the surviving artifact. The Indus civilization, flourishing around the same broad era as Old Kingdom Egypt, laid out cities on grid patterns. Streets intersected at right angles. Brick sizes followed standardized proportions. Units of length appear to have been uniform across distant settlements. Different script, different religious iconography, different political organization. Yet again, a stable base unit. It is tempting to dismiss this as inevitable. After all, the human body is universal. The forearm exists everywhere. Of course, multiple civilizations would begin with similar anthropic measures, but that explanation accounts only for origin, not for stability. The leap from body-based approximation to state-controlled standard is not automatic. It requires infrastructure. Someone must define the official length. Someone must preserve it. Someone must enforce its use. When we compare the Egyptian royal cubit to Mesopotamian and Indus units, we find differences in absolute length. They are not identical, but they fall within a narrow range, roughly half a meter, give or take a few centimeters. That range is not random. It is practical, long enough to be useful in construction, short enough to handle easily, divisible into rational fractions. And in each culture, the subdivisions display internal coherence. Palms, digits, fingers, different names perhaps, but similar logic. This recurring structure raises a delicate question. Did these systems develop independently because they represent optimal solutions to human-scale building? Or did ideas travel? Trade routes connected Mesopotamia to the Indus as early as the 3rd millennium BCE. Egyptian artifacts have been found in the Levant. Goods crossed deserts and seas. With goods come merchants. With merchants come agreements. Measurement is the language of exchange. If a merchant from one region arrives with timber or metal, quantities must be reconciled. Over time, repeated contact could produce convergence, not through conspiracy, but through necessity. Yet there is another possibility. Perhaps the similarities do not reflect direct borrowing at all. Perhaps they reflect constraints imposed by the human body and by material reality. Consider this. Stone blocks are heavy. A workable unit must be manageable for a single worker to mark. Repeatedly. Too long and the rod becomes unwieldy. Too short and measurement requires excessive repetition, increasing cumulative error. Half a meter is comfortable. It aligns with arm span, with stride, with ergonomic handling. Divide that unit into 4 parts, or 7 parts, or 10 parts. The details vary, but the instinct to subdivide into rational increments remains consistent. In other words, there may be a deeper rule at work, a convergence driven not by cultural transmission, but by physics and physiology, and yet the precision still presses upon us. In Egypt, the royal cubit remained remarkably stable across centuries. In Mesopotamia, measurement tablets reveal careful recording of unit conversions. In the Indus Valley, standardized brick ratios appear across settlements separated by vast distances. These are not fleeting experiments, they are durable systems. If we return to Giza with this broader perspective, the pyramid begins to feel less like an anomaly and more like an apex, a monumental expression of a principle shared across early civilizations. Standardization precedes scale. You cannot build a city grid without agreement on length. You cannot tax land without consistent measurement. You cannot erect a pyramid whose sides converge cleanly without disciplined units. The more we examine ancient artifacts, rods carved from wood or stone, rulers etched in ivory, tablets inscribed with length and area, the more we see that measurement was not incidental, it was foundational, and that challenges a quiet assumption. Modern narratives often frame ancient societies as technologically limited until gradual advances culminate in classical mathematics and later scientific revolutions. But the artifact evidence suggests that robust measurement systems existed far earlier than many imagine. They may not have possessed abstract symbolic notation as later Greek mathematicians did, but they possessed operational precision, and operational precision is what builds. If you find yourself wondering how many other aspects of early engineering we have understated, then remain with this inquiry. Subscribe if you choose, not for speculation, but for examination. Because the more closely we look, the more the ancient world appears structured rather than primitive. Still, attention remains unresolved. The Egyptian royal cubit is not identical to the Mesopotamian cubit. The Indus ruler divisions are not numerically the same as Egyptian palms. Absolute values differ. And yet the pattern of standardization, base unit, subdivisions, durable rods, administrative enforcement, recurs. Is this similarity coincidence, born from common human anatomy and practical constraints? Is it cultural transmission, ideas carried quietly along trade routes and reshaped to local systems? Or does it reveal something deeper, an underlying rule of construction that any organized civilization must inevitably discover? If disciplined measurement is a prerequisite for large-scale architecture, then perhaps the emergence of standardized units marks a universal threshold in societal complexity. The pyramid, then, is not merely Egyptian. It is a testament to a broader human transition from approximate building to calibrated construction. But how calibrated? When we compare artifact rods across cultures, the variation is small, yet not negligible. Each system maintains internal consistency, but differs externally, which raises the next pressing question. If civilizations could preserve stable units within their own domains, how did they maintain such tight tolerances across massive projects? What mechanisms prevented drift over decades of construction? What ensured that the cubit used in the quarry matched the cubit used on the plateau? The rods exist, the rulers survive, the bricks align, but the enforcement, the living system behind the artifact, remains partially obscured. And until we understand that enforcement, the true secret of ancient precision, remains just beyond our grasp. Measurement does not travel on its own. It moves with merchants, with caravans pressing across desert corridors, with ships hugging coastlines, with sealed jars of oil and sacks of grain and ingots of copper stacked carefully against wooden hulls. Where goods move, numbers follow. And where numbers are exchanged, agreement becomes survival. By the 3rd millennium before our era, the ancient world was far from isolated. The Nile Valley traded with the Levant. Mesopotamian city-states exchanged goods with Anatolia and the Persian Gulf. Indus merchants left seals in Mesopotamian ports. Lapis lazuli from Afghanistan has been found in Egyptian contexts. Cedar from Lebanon reached the Nile. Copper from Oman moved northward. This was not mythic globalization. It was pragmatic necessity. And trade demands measurement. If a merchant from Mesopotamia arrives in a Levantine port with a shipment of wool, the receiving party must quantify it. If Egyptian officials purchase timber from Byblos, they must verify its length and volume. Contracts cannot survive ambiguity. Over time, repeated exchange exerts pressure toward compatibility, not identical systems, but convertible ones. Archaeological tablets from Mesopotamia record detailed systems of weights and measures. Silver was weighed according to standardized units. Land was measured for taxation. Temples and palaces maintained official standards. These units were often stored physically. Reference stones, metal weights, master rods. In Egypt, similar administrative precision appears. Grain storage was calculated carefully. Labor rations were allotted by measure. Construction planning relied on consistent units, and in the Indus Valley, standardized brick dimensions, often in a consistent ratio, appear across cities separated by hundreds of kilometers. Such uniformity implies agreement, and agreement implies communication. Trade routes are not merely economic arteries, they are intellectual conduits. When merchants meet, they compare. When officials negotiate, they reconcile differences. A cubit in one region may not match exactly in another, but the need to translate units fosters awareness of proportional systems. Imagine a Mesopotamian trader encountering Egyptian surveyors. Even if their cubits differ slightly in length, both are subdivided rationally. Both rely on repeatable segments. Both recognize the importance of maintaining consistency. The encounter does not require one civilization to dominate another. It requires only sustained contact. There is no evidence of a single unified ancient measurement authority stretching from the Nile to the Indus. But there is abundant evidence of interaction, and interaction shapes systems. Economic necessity is a powerful harmonizer. Consider the logistics of large-scale trade in metals. Copper ingots must be weighed, transported, accounted for. Discrepancies would provoke dispute. Standardized weights, often shaped and stamped, have been discovered across the Near East. Some show remarkable consistency across wide geographic areas. Length units are harder to trace archaeologically than weights, but the principle remains similar. If you are exporting timber beams, their dimensions matter. If you are constructing ships based on shared design knowledge, proportional systems become embedded in practice. Measurement systems can migrate subtly, not as imposed doctrine, but as adopted convenience. Over generations, what begins as foreign adaptation becomes local tradition, but here we must guard against overreach. Similarity does not prove direct borrowing. The Egyptian royal cubit is longer than many Mesopotamian cubits. Indus rulers show their own distinct calibration. Each civilization maintained autonomy. The convergence lies not in identical values but in structural logic. Base unit derived from the body, subdivided into manageable parts, preserved in physical form, administered through institutions, applied rigorously in construction. This pattern repeats. Trade may have reinforced awareness of standardized practice, but even absent direct exchange, any society reaching a certain level of complexity would face the same pressures. Urban planning demands order. Irrigation canals require consistent gradient. Monumental architecture demands uniform block sizing. In other words, measurement standardization may be less a cultural luxury and more a developmental threshold. Once crossed, it transforms what a society can build. Return now to Giza. The Great Pyramid did not emerge from isolation. Egypt was engaged in trade networks long before Khufu's reign. Copper from Sinai, timber from Lebanon, exotic materials from Nubia and beyond. Managing such networks required quantification. If Egyptian administrators were already accustomed to standard weights and measures in trade, applying similar discipline to construction becomes plausible, even inevitable. The pyramid then is not a miracle of sudden precision. It is an apex expression of a culture already steeped in calibrated exchange. Yet there remains a subtle mystery. Trade explains awareness. Trade explains compatibility. Trade explains pressure toward rational systems. But does it explain the extraordinary tightness of tolerance we observe at Giza? The pyramid's orientation, its leveling, its dimensional consistency, these are not merely sufficient for commerce. They exceed what trade would demand. No merchant requires alignment to true north within 3 arc minutes. No caravan insists on centimeter precision across, hundreds of meters. So trade may explain the spread of measurement culture. But it doesn't fully account for the ambition of monumental exactness. If you find this widening context compelling, if the idea that commerce quietly shaped civilization's capacity for precision resonates, then stay with this exploration. Subscribe if you wish, not for spectacle, but for the careful threading of cause and effect. Because the story of measurement is the story of order imposed upon chaos. And order, once discovered, tends to expand. How far did measurement knowledge travel? Did it reach across deserts and seas, subtly harmonizing construction practices across cultures? Did it influence city planning, temple orientation, administrative law? Or were these systems emerging independently, driven by universal constraints of human anatomy and material reality? The evidence suggests contact. The artifacts suggest structure, the monuments suggest mastery. But the full map of transmission remains incomplete. And as we trace these routes further, from port to plateau, from ledger to limestone, a deeper question begins to form. If standardized measurement became the backbone of ancient trade and architecture, how did these societies guard against error at scale? How did they prevent drift across decades? Because influence explains spread. It does not yet explain control. And control, over distance, over direction, over dimension, is what truly defines the Great Pyramid's enduring precision. So we must now turn from exchange to enforcement, from contact to correction. For somewhere within that transition lies the next piece of this measured enigma. We have traced measurement along trade routes, across deserts and rivers, from Egypt to Mesopotamia, from the Indus to ports along the Persian Gulf. We have seen how standard units and disciplined recording allowed distant cultures to coordinate commerce, build temples, and lay out cities. And yet, measurement alone is only the first step. Knowing how long a cubit is or how many palms it contains does not by itself produce the lines, angles, and proportions that transform stone and brick into lasting monuments. To go further, we must consider geometry, not as abstract theory, but as embedded practice. And remarkably, the traces of such practice extend far beyond the Nile. Archaeologists have long noted that pre-Columbian Pueblo sites in what is now the American Southwest display geometric regularities that are difficult to dismiss. Circular kivas, rectangular dwellings, and even entire village layouts often conform to proportions that suggest more than happenstance. The spacing between structures, the alignment of doorways, and the orientation of plazas reveal patterns that resemble intentional layout rules. Measurements of multiple sites indicate repeated ratios, rectangles of similar proportions, consistent angles at corners, even recurring diameters for communal structures. The initial assumption might be that these were practical choices, that certain building dimensions were convenient for human use. Certainly, ergonomics plays a role, but the repetition of proportional relationships across settlements separated by tens of kilometers hints at an underlying logic, something akin to a shared syntax for spatial organization. What is remarkable is that these patterns arise without evidence of written instructions or formal mathematical texts. Unlike Egypt or Mesopotamia, the Pueblo builders left no surviving codified system of measurement. Yet their constructions suggest that knowledge of relative proportion, alignment, and angle was applied systematically. Similarly, other sites across the globe, from megalithic circles in Europe to early settlements in South Asia, show hints of consistent geometric planning. Stone circles, long barrows, and temple platforms frequently adhere to alignments along cardinal points, specific angular separations, or repeated ratios that ensure symmetry and balance. In these cases, geometry emerges not as theoretical abstraction, but as an operational tool, a way to translate a plan into space, to coordinate multiple builders, and to achieve enduring forms. This suggests a crucial insight. Geometry is not necessarily learned in classrooms or written in treatises. It can exist as practice, a kind of operational knowledge embedded in the craft of building. Repetition, observation, and incremental adjustment over generations may yield surprisingly sophisticated patterns, and yet, when we compare these distant practices, a question arises. The same principle of proportionality, the same drive toward right angles, repeated ratios, and alignment with the environment appears again and again. Across cultures separated by oceans, deserts, and millennia, builders demonstrate a remarkably similar approach. Define a baseline, subdivide it rationally, check angles repeatedly, and construct in proportional units. We might call this a geometry syntax, a set of tacit rules that governs how space is divided, how walls and plazas relate, how structures maintain balance and alignment. It is a silent language, transmitted not in writing, but in the continuity of practice. Returning to the Near East and Giza, the parallels are striking. Egyptian architects measured cubits, laid baselines, applied the secked, and maintained a level plane over enormous distances. Mesopotamian surveyors calculated canals, temple foundations, and city streets. In the Pueblo settlements, architects applied proportional rules to align rooms, plazas, and ceremonial spaces. The methods differed in material, scale, and context, but the underlying principle remains: systematic, proportion-driven construction. Could these recurring patterns suggest that human cognition naturally converges on certain spatial rules when tasked with building? Perhaps. Practical constraints of labor, material, and human ergonomics may channel independent cultures towards similar solutions. Rectangles are stable, right angles are strong. Repeating a reliable ratio ensures symmetry and predictability. Yet the consistency in execution often exceeds what pure intuition would produce. The Pueblo kivas, laid out precisely and repeatedly, the pyramids leveled to within centimeters, the Mesopotamian ziggurats, constructed with proportional brick courses, all suggest the operation of rules codified, taught, and enforced. Even without written geometry, builders were applying a common grammar of spatial relationships. If human societies across the world developed these proportional systems independently, is it coincidence, or does it reflect a universal logic of construction? Is there, embedded in the act of building, a shared syntax for geometry, a cognitive toolkit that all humans draw upon when translating measure into form? We see echoes of this geometry syntax in different eras and continents: precise angles, repeated ratios, cardinal alignment, and modular repetition. But the question remains, could this have been transmitted consciously or subconsciously across regions separated by vast distances? Or is it an emergent property of human design, the inevitable solution that arises whenever people attempt to order space reliably, to coordinate labor, and to create enduring structures? As we prepare to examine the next layer of evidence, we will return to the pyramid, where this question becomes most acute. There, the codified cubit, the secked slope, and the meticulously leveled baseline combine to produce a structure that is not only immense, but also geometrically coherent. And when we measure these proportions in modern terms, we encounter the tension between practicality and apparent mathematical sophistication. For now, the Pueblo sites, the European megaliths, the Indus settlements all hint at the same phenomenon. Builders, given constraints of material, labor, and social coordination, discover proportional systems. These systems are repeatable, they are durable, they are measurable. But the extent to which such systems constitute a universal syntax, a shared framework for translating measure into structure, remains uncertain. The stones and adobe walls do not tell us directly, they only preserve the result. The knowledge of process, teaching, verification, and correction remains mostly invisible. And so, we arrive at the tension that drives the next stage of our journey. If such proportional knowledge was latent across multiple civilizations, if it appeared in both isolated and connected cultures, what does that imply about the foundations of architecture itself? Did ancient builders, separated by geography and culture, independently discover a common grammar for organizing space? Or did ideas of proportion and measurement migrate quietly along trade and contact networks, shaping construction techniques far beyond Egypt? The answer, it seems, may lie buried not in myth, but in the stones themselves, and in the methods by which those stones were raised, measured, and aligned. And as we prepare to turn back to the pyramids themselves, the question lingers. Did a universal geometry syntax exist, waiting to be discovered, quietly guiding human hands across continents and millennia? The desert wind erodes the edges, the sand shifts, and yet the base of the Great Pyramid remains astonishingly true. Surveyors have measured it repeatedly. The four sides differ by mere centimeters, a deviation so small that it amounts to less than 1/20% of the total length. Over 230 meters per side, the total variation is scarcely more than a hand's breadth. Across millennia, a base leveled on uneven limestone bedrock has maintained this perfection. This is no ordinary feat. To understand why, we must consider the tools available to the builders. Copper chisels, wooden leveling devices, plumb bobs, ropes and rods comprise their instrument set. Ingenious as they were, these instruments introduce natural variation. Ropes stretch, wood warps. Even water levels, if left exposed to sun and evaporation, fluctuate. And yet the pyramid's base shows variation far smaller than the sum of these potential errors would predict. Statistical expectations would suggest greater drift. When thousands of blocks are quarried, transported, and set across a large platform, each stage introduces cumulative deviations. A modest error in a single stone's placement, multiplied across rows and layers, should result in visible distortions. Over a base spanning more than 2 football fields, even a small misalignment in one corner should propagate into noticeable skew. Yet the measurements reveal the opposite. Surveyors such as Flinders Petrie and more recently laser and total station analyses confirm that the corners meet almost perfectly at right angles. The base is nearly a true square. The level is so uniform that over hundreds of meters there is scarcely a discernible slope. The difference between the highest and lowest points of the base is measured in mere centimeters. This precision defies conventional expectation. By the standards of other contemporary construction projects, even the best organized labor forces, with copper tools and no modern optical instruments, would have produced deviations at least an order of magnitude greater. The margin of error achieved at Giza is extraordinary. Part of the explanation lies in standardization. The royal cubit provided a uniform unit, ensuring that measurements in the quarry, on transport sleds, and at the construction site were consistent. Cubit rods, carefully calibrated and periodically checked against master standards, allowed foremen to maintain repeatable lengths. When placing stones, teams could measure courses accurately, preserving intended proportions. Yet even with standardized units, maintaining such uniformity across a base that stretches for more than 900 feet on each side is remarkable. Human error alone should have been significant. Differences in sighting, uneven terrain, variations in tension on ropes, and minor misreading of rods would accumulate. And still, they did not. Another factor is repetition and verification. Evidence from the plateau suggests that measurements were checked constantly. Ropes may have been stretched and re-stretched, wooden rods compared against master cubits, diagonals of the square repeatedly measured to confirm right angles. Errors, when detected, were corrected immediately. The process would have been slow, laborious, and methodical, the very opposite of improvisation. Even so, the statistical improbability remains striking. The methods available, while clever, should have introduced more variation. The observed uniformity implies not only diligence, but technique, a procedural system that consistently reduces error below what conventional estimation predicts. Consider the leveling of the base. Modern experiments demonstrate that using water-filled trenches or simple sighting instruments can produce reasonable flatness over small distances. Over hundreds of meters, however, natural irregularities in rock and ground settle in. Yet at Giza, the base is flat to within mere centimeters. Whether by repeated water leveling, channeled guide trenches, or other surveying methods, the builders achieved control beyond what casual experimentation would allow. This precision is not merely aesthetic, it has structural consequences. A misaligned base would propagate errors upward, affecting the angles of the faces, the placement of the apex, and the stability of the structure. Maintaining accuracy at the foundation allowed the pyramid to rise symmetrically and endure millennia of weather and erosion. The cumulative implication is profound. The combination of standardized measurement, disciplined labor, and repeated verification was sufficient to constrain error to astonishingly low levels. But conventional analysis of the tools suggests that even these practices alone might not fully account for the observed uniformity. In other words, there is a measurable contradiction. The technology available, copper tools, wooden rods, ropes, and plumb bobs, statistically should have produced greater deviations. Yet the pyramid's base exhibits tolerances that exceed expectations. The discrepancy is subtle but undeniable, the achievable error width. The instruments of the era is larger than the actual error measured in the finished work. This raises a compelling question. Were there additional techniques, now lost to history, that allowed workers to maintain this precision? Did they develop methods of measurement or correction that functioned across scales far larger than any simple rope or rod? Or was the process of redundancy and verification so rigorous, so methodically repeated, that human error became almost negligible? The answer remains uncertain, but the fact is measurable. We can observe the base. We can record the deviations. We can compare those deviations to the expected performance of contemporary instruments. The numbers speak. They reveal a level of control that should have been statistically improbable. The Great Pyramid's foundation is not just a base. It is a testament to systematic accuracy, to procedures that translate units into alignment and into enduring form. It reflects an understanding, whether practical, procedural, or experiential, of how to constrain error at an unprecedented scale. And as we step back to consider the broader implications, a pattern begins to emerge. Measurement, standardization, proportional systems, trade influences, and geometric practice all converge here. The pyramid's base is where theory meets execution, where abstract cubits meet the real world, and where the human capacity for precision is tested against the limits of available technology. Yet the question lingers. If the tools themselves should produce larger errors, what hidden discipline, method, or technique allowed builders to reduce variation to such a minimal level? Was it an unrecorded procedure, a refined calibration practice, a layer of redundancy and oversight so meticulous that human error was systematically neutralized? Whatever the answer, it emphasizes the fundamental point. The Great Pyramid is more than a monument. It is a measurable record of precision that challenges assumptions about what was achievable with the instruments of its time. The stones, the rods, the ropes, all testify not only to ambition, but to a command of error, to a management of variance that modern analysis finds extraordinary. And so the base, leveled and true, leaves us with a pressing thought. Beneath the apparent simplicity of ancient tools lies a discipline capable of controlling error at a scale that seems, by conventional expectation, impossible. The question of method, how error was constrained beyond what the technology should allow, now presses directly upon us, demanding further exploration. The pyramid has long invited the human mind to look for patterns. Its soaring faces, its perfect square base, its apex pointing skyward. These features suggest order, symmetry, and proportion. And in that order, generations of observers have glimpsed numbers that seem almost magical. Ratios reminiscent of the golden proportion, approximations of the circle constant, even subtle harmonies of height and perimeter, all have been suggested as evidence of knowledge far beyond what we imagine of ancient Egypt. Yet measured carefully, the story is far more grounded. When we step away from the allure of symbolic fascination and examine the data in the units the builders themselves used, a more cautious picture emerges. The pyramids were constructed in cubits, subdivided into palms and digits. The slope was determined by the secked, the base was leveled with painstaking care. All of these are tangible physical measures, not abstractions. The golden ratio, familiar to many as a proportion of about 1 to 1.618, has been invoked repeatedly in attempts to read hidden sophistication into the Great Pyramid. It appears that if one compares half the base to the height, the resulting number comes close to that familiar value. But close is not exact. When we measure the pyramid in royal cubits, the ratio is not a precise 1.618. It is a convenient fraction, arising naturally from the chosen slope, 5.5 palms per cubit. The secked system produces proportions that are tidy in terms of whole cubits and fractions. From a modern perspective, these proportions happen to resemble a famous constant. But in the world of Old Kingdom architects, they were functional, not philosophical. Pi, too, is often cited. Observers note that the perimeter of the base divided by twice the height yields a number approaching the circular constant. Yet again, this is a consequence of cubit-based design, of the selected slope and course height, and of practical construction choices. The builders were not calculating circles. They were building a square, a stable structure with precise angles and levels. That an emergent ratio aligns closely with a constant recognized millennia later is fascinating, but it is not evidence of deliberate calculation. In fact, when we measure the pyramid in centimeters or meters, translating ancient cubits into modern terms, minor adjustments in slope or course height produce noticeable changes in these derived ratios. A single palm more or less per cubit, or a slight variation in leveling, shifts the value away from any resemblance to pi or phi. The apparent precision of these constants is therefore highly sensitive to interpretation. Archaeologists and historians approach these claims cautiously. Surviving texts from the Old Kingdom, mathematical papyri, accounting records, and architectural notes contain no explicit reference to theoretical constants. The Egyptians understood fractions, practical geometry, and the relationships necessary for construction, but their written records show no conceptual knowledge of a universal circle ratio or the golden proportion. What we do see is a culture profoundly skilled at measurement and proportion. The choice of slope, the dimensions of base and height, and the alignment of stones were governed by rules that are physical, not symbolic. These rules ensured structural stability, coordinated labor, and achieved visual harmony. The neatness of the numbers in cubits allowed calculations and verifications to be repeated easily by multiple teams over decades of construction. It is also important to recognize human pattern recognition. Observers are inclined to find significance in numbers that appear familiar. Modern knowledge of pi or phi is retroactively imposed on measurements that were never intended to encode them. This does not diminish the skill of the builders, it merely reminds us that interpreting ancient design through the lens of modern mathematical concepts can be misleading. When we measure the pyramid precisely, the base remains almost perfectly square. The slope is uniform across faces. The sides converge on a single apex. The angles at corners are near right angles. These are measurable facts, verifiable and consistent. They are the result of disciplined application of measurement rules, not mystical encoding of constants. What is more revealing is the consistency across other monuments. Smaller pyramids, step structures, and temples follow similar proportional practices. Slope, height, and base dimensions are expressed in whole cubits or simple fractions. Differences between monuments are small, often reflecting functional adjustments rather than theoretical experimentation. The Egyptians were practical builders, applying a coherent system that produced reliability at scale. And yet, the tension remains. The neatness of the ratios, the apparent elegance in proportion, the near-perfect alignment with cardinal points, these features naturally invite speculation. If not intentional mathematical constants, then what dictated the design choices? The answer appears to lie in the rules themselves: standard units, fractional subdivisions, slope conventions, and proportional guidance. Builders used the royal cubit as a baseline, measured distances with rods and ropes, determined angles with plumb bobs and sighting devices, and controlled vertical rise and horizontal run through the secked system. The consistency of these practices produced ratios that, when translated into modern measures, approximate constants familiar to us. But those constants were a byproduct, not a design goal. The same principle emerges in other cultures as well. Mesopotamian ziggurats follow proportional layouts suitable for stability and ceremonial function. Indus Valley cities use modular brick sizes and street grids that preserve visual and functional harmony. Pueblo settlements apply repeated ratios in their building layouts. In each case, the resulting forms suggest order and balance, yet there is no evidence of explicit knowledge of universal mathematical constants. In short, measurable design was achieved through discipline and standardization, not through theoretical abstraction. The pyramids, monumental as they are the tangible outcome of operational rules, a language of measure and proportion embedded in practice. The ratios that fascinate modern observers emerge naturally from this language. And so we arrive at the subtle question that frames our next step. If not intentionally encoding constants, if these ratios arise from practical rules and standardized units, then what governed those rules? Were they inherited from earlier constructions, derived from observational study of stability and aesthetics, transmitted through training and apprenticeship? The pyramids, measured carefully, reveal the answer in part. The rules were embedded in practice, reinforced through repetition, and maintained across decades and generations. But the underlying logic, why certain slopes, ratios, and proportional conventions were chosen, remains tantalizingly close to the boundary between observed fact and human inference. The stones speak of consistency and proportion. They hint at a system of rules that guided every course, every corner, every alignment. And as we move deeper into the evidence of shared measurement practices across civilizations, the question presses further: what principles, practical or cognitive, underpinned the remarkable design decisions that allowed builders to achieve harmony at monumental scale? Share your thoughts in the comments section. Across the desert, the Great Pyramid rises, a testament not only to vision but to discipline. Its sheer scale is staggering. Hundreds of thousands of limestone blocks, each weighing tons, had to be quarried, transported, cut, and positioned with care. But the monument's endurance, its precise base, its uniform slope, its symmetrical faces, is not explained by vision alone. It is explained by process, by standardization, by the careful management of complexity on a scale that few societies, ancient or modern, have matched. Central to that process was measurement. The royal cubit was more than a unit of length. It was a foundation for coordination. Workers could not improvise. They required a common language of measure that would hold across time, space, and teams, and that language had to be preserved with extraordinary care. The evidence suggests it was. Cubit rods, carved in wood or stone, were maintained as master standards. These rods were often checked against official reference lengths, possibly stored in temples or administrative centers. Periodically, calibration ceremonies may have been held. Scholars have hypothesized that these involved comparing rods, marking deviations, and confirming that each work crew's instruments matched the master reference. Such practices ensured that a cubit measured in the quarry was the same cubit applied on the pyramid's plateau. This was not a casual procedure. Standardization required oversight, a chain of responsibility, and institutional authority. Foremen, inspectors, and scribes may have monitored the construction, verifying lengths, checking angles, and confirming that measurements aligned with the master plan. The hierarchy of control implied by these practices mirrors, in principle, modern quality assurance systems: a standardized unit, repeated verification, corrective measures, and documentation of compliance. Consider the scale of the task. The pyramid's base stretches more than 230 meters on each side. Over such a distance, even minor deviations in measuring rods or errors in alignment would accumulate rapidly. If unchecked, the corners would not meet, the faces would bow, and the apex would fail to converge. Standardization was the mechanism that prevented this cascade of error. Workers likely employed multiple checks at each stage. When laying courses of stone, teams could measure from baseline markers, cross-check against master rods, and sight along aligned strings or plumb lines. Errors were corrected immediately rather than allowed to compound. Repetition and redundancy were embedded into the workflow. This reflects a sophisticated understanding of cumulative error, a concept familiar to modern engineers, but remarkable in its execution thousands of years ago without mechanical instruments. The comparison to modern project management is striking. Today, large-scale construction projects employ quality control teams, calibration of instruments, digital measurement, and documentation to ensure consistency. Ancient Egyptian builders did not have lasers or digital sensors, yet they appear to have developed a parallel system within the limits of their technology. Tangible instruments, human oversight, procedural checks, and hierarchical authority. Evidence for this approach comes from several sources. Surviving cubit rods, sometimes finely graduated, demonstrate careful production and durability. Archaeological accounts suggest temple workshops and scribal offices maintained standard measures, distributing copies as needed. And the outcome, not only the Great Pyramid but other Old Kingdom structures, provides empirical confirmation. Levels, slopes, and alignments consistently fall within surprisingly narrow tolerances. The implication is profound. Standardization was not an abstract ideal, it was operational. It enabled coordination of thousands of laborers over decades. It translated architectural vision into physical reality, and it mitigated the limitations of human error. Yet this system raises further questions. If so much care was invested in maintaining measurement integrity, how far did oversight extend? Did supervisors monitor every stone? Did crews follow checklists, passing measurements up a chain of responsibility? Did institutional rituals reinforce compliance? The evidence is suggestive but incomplete. Modern engineers would call this quality assurance. It is tempting to describe it in those terms, but the Egyptians likely did not. Their system was embedded in culture, labor organization, and ritual. Measurement and verification may have been tied to social hierarchy, religious duty, or communal responsibility. Calibration ceremonies, for example, could reinforce both technical accuracy and social cohesion, ensuring that deviation from the standard was socially as well as practically unacceptable. The repeated use of master rods across sites further supports this notion. The same cubit standard appears in multiple projects over decades, suggesting that institutional knowledge persisted, transmitted not only through artifacts but through training and oversight. Craftsmen would learn the system, apprentices would inherit it, and foremen would enforce it. The result: consistency across time and scale. From a modern perspective, it is remarkable to consider the sophistication of this approach. Large projects today still struggle with variance, misalignment, and cumulative error. The Egyptians managed these risks with tools of wood, stone, and rope, guided by principles of repeatable measurement and careful verification. The scale, precision, and durability of their monuments provide compelling evidence that this system functioned effectively. Yet, as with all ancient practices, uncertainty remains. We do not have written manuals describing procedural steps in detail. We do not know the frequency of inspections or the exact methods for correcting deviations. Much of the system is inferred from the combination of surviving artifacts and the extraordinary outcomes they produced. Still, the measurable reality speaks clearly. The pyramids, quarries, and administrative records collectively suggest a culture capable of controlling complexity in ways that rival some modern practices. Standardization was not theoretical. It was lived, applied, and verified continuously. And here emerges the pressing question. If the Egyptians could implement such a system without modern instruments, what techniques ensured that error did not accumulate? How did they maintain control over thousands of stones and hundreds of meters, guaranteeing that the base remained square, the slopes uniform, and the apex aligned? It is one thing to have rules, it is another to enforce them reliably across decades and vast workforces. The existence of master cubit rods, calibration rituals, and institutional oversight implies a form of quality control. But was it sufficient to explain the extraordinary precision of the Great Pyramid's construction? The answer remains tantalizingly out of reach. The system of measurement and verification clearly existed. It was applied, it was disciplined, and yet the resulting tolerances surpass what might be expected purely from the technology and materials available. In that tension lies the heart of the puzzle. A society capable of rigorously applying standardized measures, managing complex workflows, and maintaining astonishing accuracy, all without modern instruments or digital record-keeping. The pyramids are the proof. And they leave us wondering, how complete was their system of quality control, and what principles allowed it to function so effectively? Across continents and millennia, a curious pattern emerges. From the limestone quarries of Egypt to the clay bricks of Mesopotamia, from Indus Valley rulers to Pueblo settlements, builders repeatedly return to similar proportions, recurring base units and standardized subdivisions. At first glance, it appears that human societies, separated by geography and time, may have shared measurement systems. Yet the deeper question is more subtle. Are these similarities evidence of direct transmission, or do they arise from universal constraints imposed by materials, human physiology, and the practicalities of construction? Statistical reasoning allows us to move beyond anecdote. By comparing measurements from dozens of sites, scholars can quantify variation in base units, ratios, and proportional systems. For example, the Egyptian royal cubit, approximately 52.3 centimeters, differs from Mesopotamian cubits by only a few centimeters. Indus Valley rulers exhibit subdivisions that are remarkably consistent across hundreds of kilometers. Pueblo kiva diameters and room dimensions fall within a narrow range of ratios. When examined collectively, these patterns are not scattered randomly. They cluster around similar values, but clustering alone does not prove shared. Standards. Human scale constraints create natural limits on workable unit sizes. A half-meter cubit, give or take a few centimeters, is ergonomic. It can be measured, lifted, and applied repeatedly. Stones and bricks can be manipulated efficiently within this span. Longer units risk unwieldy handling. Shorter units require excessive repetition and increase cumulative error. Proportions that create right angles, symmetrical forms, or balanced structures are likewise constrained by gravity, material stability, and labor practices. Herein lies the statistical tension. When analyzing multiple civilizations, some variation is expected. If each society were experimenting independently, we would anticipate a broader dispersion of unit lengths and proportional ratios. Yet the observed distributions are narrower than random experimentation predicts. Across vast distances, similar base units recur, ratios approximate simple fractions. The convergence is tighter than what physical ergonomics alone would generate, though not identical. This is where statistics can illuminate. Using measures of central tendency and standard deviation, we can evaluate whether the clustering of units and ratios exceeds what chance and practical constraints would predict. In many cases, the probability that such patterns arise purely from independent ergonomic constraints is low. There is a signal here, a measurable coherence, even if it falls short of proof for direct transmission. Consider the Great Pyramid alongside Mesopotamian ziggurats and Indus city grids. Each employs a modular system of units, subdivided rationally with remarkably consistent dimensions across their respective landscapes. The likelihood that such modularity and repeated fractional subdivision emerge independently with such precision is small. Yet the differences, the Egyptian cubit is not exactly the Mesopotamian cubit, Indus bricks are not identical, indicate adaptation rather than exact copying. There is convergence, not perfect replication. From a statistical perspective, we might call this a case of constrained convergence. Similar solutions arise in response to shared physical, ergonomic, and structural pressures. Human hands can only reach so far. Stones only bear so much weight. Labor coordination favors modular systems. Across multiple civilizations, these constraints guide the emergence of comparable units and proportional schemes. But within that framework, culture, trade, and institutional practices refine and stabilize the measurements. The challenge lies in interpretation. When does similarity move from coincidental convergence to meaningful pattern? Scholars debate thresholds. If two civilizations share units within a centimeter, with proportional ratios aligning across multiple constructions, the probability of independent invention diminishes. If similarities extend across multiple regions and multiple types of structures, residential, ceremonial, monumental, the evidence for shared principles or even transmission strengthens. Yet caution is warranted. Statistical coherence does not imply intentional coordination across continents. It may indicate universal principles of efficiency and ergonomics, refined by local cultural practice. The Great Pyramid, then, exists within a broader statistical landscape, one in which repeated patterns of measurement, proportion, and subdivision emerge from both constraint and cultural codification. The tension sharpens when we examine precision. The base of Giza, squared to less than 0.05% variation, exceeds what we find in contemporaneous Mesopotamian and Indus structures. This suggests that while similar principles may operate broadly, the degree of accuracy achieved in a single project can surpass the general trend. Precision, not just proportion, becomes a distinguishing factor, highlighting the mastery of process and oversight in addition to convergent unit selection. From this perspective, the unity of measurement patterns is both practical and philosophical. Practical, because shared human constraints favor similar unit sizes and proportional systems. Philosophical, because repeated observation across cultures reveals a subtle thread. When societies standardize, subdivide, and apply consistent units, they create structures that endure and communicate order. Statistical analysis shows that these patterns are unlikely to be mere coincidence, yet they are not uniform, leaving room for adaptation, creativity, and localized refinement. Thus, the analysis presents a dual narrative. On one hand, universal constraints guide the emergence of similar base units and ratios, producing measurable patterns across independent societies. On the other hand, deviations from exact replication paired with exceptional precision in some cases indicate local innovation, procedural mastery, and potentially the influence of contact and trade. The broader implication is profound. The similarities we observe are neither accidental nor purely symbolic. They are measurable, they are testable, and they reveal that ancient societies, despite geographic separation, repeatedly discovered solutions that balance human scale, material limits, and structural integrity. And yet, a question remains. When does similarity become significant enough to suggest shared knowledge rather than convergent problem-solving? At what point does statistical clustering reveal a universal principle embedded in human construction rather than the natural consequence of practical necessity? The answer is not absolute, but it frames the next step of our inquiry. By examining the rules and techniques that produced both proportion and precision, we begin to see the architecture not just as isolated monuments, but as expressions of disciplined knowledge that may echo across civilizations, bridging gaps of distance and time. The stones themselves remain silent, but the patterns measured, compared, and analyzed speak loudly. And as we proceed, we must ask, what hidden rules governed their design, and how did these rules combine with human ingenuity to achieve precision that challenges our understanding of ancient capability? The stones of the pyramid have long been silent witnesses to human ambition. Yet when we measure them, they speak in unmistakable numbers. Each block, each course, each corner carries evidence of a precise plan executed with extraordinary control. And it is in those measurements that the central tension of ancient engineering emerges, a tension between what was achieved and what conventional assumptions suggest was possible. Consider first the cubit. The royal cubit, the fundamental unit of Egyptian construction, recurs relentlessly across the Great Pyramid. Surveyors have measured courses, walls, and internal chambers. The dimensions align with remarkable consistency. Deviations are small, fractions of a cubit over lengths spanning tens of meters. For a society wielding wooden rods, ropes, and plumb bobs, this degree of repeatability is remarkable. Human error alone should have produced wider variation, yet the builders maintained accuracy to within a few millimeters across hundreds of stones. Next, the base. Its four sides, each extending over 230 meters, converge to form a square with corners almost perfectly right-angled. Modern surveying confirms the variation along the perimeter is less than 1/20%. To visualize this, imagine measuring across a football field and finding the corners differ by no more than the width of a human hand. The rock beneath is uneven, the surface is not naturally flat, and yet somehow the pyramid's foundation is leveled with extraordinary precision. Orientation is equally striking. The sides align with the cardinal points, north, south, east, and west, with a deviation of just a few arc minutes. Ancient Egyptians had no magnetic compasses. They had no theodolites, no optical surveying devices of the kind that modern engineers rely upon. How then, with plumb bobs, sighting rods, and careful observation, did they achieve alignment that approaches the accuracy of contemporary instruments? Error margins compound the puzzle. Each block placed is an opportunity for misalignment. When multiplied across more than 2 million stones, one might expect deviation to accumulate rapidly, yet the finished structure exhibits variation far below what the tools alone would predict. This is measurable fact. Repeated cubit application, rigorous leveling, and careful alignment produce tolerances that should, statistically, have been impossible using the known technology. Other features reinforce this contradiction. Internal chambers and passageways, often hidden from view during construction, are oriented and dimensioned with similar care. Slopes, such as those in the King's Chamber and Grand Gallery, maintain proportionality with surprising regularity. Cross-sections, when analyzed in modern terms, reveal consistency that exceeds what simple empirical observation could guarantee. When we contrast these facts with assumptions about the technological capacity of the Old Kingdom, the discrepancy becomes stark. Standard narratives often suggest that large-scale precision was limited by material constraints, human error, and a lack of abstract mathematics. Copper tools, wooden measuring rods, and laborers reliant on visual judgment should have imposed much wider error margins. Yet the empirical measurements challenge this assumption. The tension is quantifiable, the data do not lie. The pyramid is squared and leveled far more precisely than conventional expectations predict. Its orientation is more exact than casual surveying methods would allow. Its proportional systems, height to base, course thickness, internal chamber dimensions, exhibit coherence that implies repeated verification and disciplined application of measurement standards. Even broader comparisons reinforce the point. Mesopotamian ziggurats, Indus city grids, and other contemporary structures, while exhibiting modular units and proportional planning, do not approach the level of absolute precision seen at Giza. Here, the combination of consistent cubit application, low error margins, and orientation accuracy coalesces into a measurable engineering fact. Ancient builders were capable of controlling variables across massive scales in ways that challenge assumptions about their tools and methods. This is not a matter of speculation or mystical interpretation. It is measurable, repeatable, verifiable. Modern surveys, laser scans, and archaeological measurements consistently reveal the same patterns. Accuracy is not isolated to a single face, course, or feature. It is embedded in the structure as a whole. The implication is profound. If our models of Old Kingdom technology suggest that cumulative error should have been greater, yet the pyramid demonstrates the opposite, then the gap must be accounted for. Either our understanding of procedural techniques is incomplete, or the ingenuity of ancient builders exceeded conventional expectations. Likely, it is a combination of both. The processes, repeated measurement, verification, calibration, oversight, functioned at a level of sophistication sufficient to mitigate cumulative error far beyond what tools alone would allow. In short, the engineering facts of the Great Pyramid, repeated cubit precision, near-perfect leveling, cardinal alignment, and minimal error margins, are at odds with the assumptions of technological limitation. They demonstrate not only ambition, but also a practical mastery of measurement, process, and quality control. This is a measurable contradiction. What was achieved exceeds what our understanding of available instruments and knowledge would suggest. And that brings us to the critical question. If these builders were capable of such precision, how did they accomplish it? Was it the result of procedural rigor, institutional oversight, iterative correction, or a combination of techniques now lost to history? Did they develop experiential methodologies that modern analysis cannot fully reconstruct? Or does this evidence compel a reassessment of what ancient societies were capable of achieving with disciplined organization and standardized measurement? These are not questions of speculation. They are questions grounded in data. Every centimeter, every cubit, every angle reinforces the anomaly. The pyramid embodies an engineering capability that challenges conventional narratives. And as we reflect on this measurable tension between expectation and result, we are confronted with a larger implication. Ancient engineering in practice may have been far more precise, sophisticated, and systematic than we typically credit. The stones, the cubits, the aligned faces, they speak a clear language. It is a language of capability. And yet, it leaves one question pressing upon us more urgently than any other. If such mastery existed, why do the methods remain largely invisible to history? The pyramid does not reveal its process directly, but it compels us to recognize that within the constraints of known tools, within the framework of labor, and under the guidance of standardized measurement, ancient engineers achieved outcomes that challenge the assumptions of our own understanding. And as we turn to consider the broader implications for architecture, civilization, and the transmission of knowledge, we must confront a central tension. Precision, process, and practice coalesce to produce measurable contradiction. The question lingers, waiting for analysis, reflection, and deeper study. What does this mean for our understanding of ancient engineering capability, and how might it reshape the narrative of human technological achievement?
They are invisible to the casual observer. Yet without them, the stones would lie scattered, the base uneven, the apex never formed. They are the men and women who measured, marked, quarried, carried, and fitted each block, the human machinery behind the monumental vision. Not mythic figures, not abstract engineers, but craftsmen, scribes, and overseers who translated the abstractions of cubits and ropes into enduring form. Their story is the story of expertise, passed down through apprenticeship, observation, and painstaking repetition. In the workshops of Memphis, master builders likely began with the cubit rod, the standard of measure that governed the project. These rods were not merely instruments, they were repositories of knowledge. Their markings, precise to fractions of a cubit, allowed foremen to convey standards across teams separated by time and space. Craftsmen learned to interpret the marks, to subdivide measures into palms and digits, and to apply them consistently in the quarry, on transport sleds, and upon the plateau itself. Apprentices observed, memorized, and practiced. A young laborer would begin by assisting in small measurements, gradually learning the rhythm of precision, how to align blocks, check levels, or sight along a baseline. Errors were corrected immediately, not abstractly, but with the tactile understanding that one misaligned stone could cascade into cumulative deviation. Knowledge was embodied in hands and eyes, in posture, in the careful repetition of method. Overseers played a crucial role. They monitored crews, confirmed measurements, and enforced the rules of proportion. Their authority was not merely managerial, it was technical. They were familiar with the limitations of the tools, the warping of wood, the stretching of rope, the subtle shift of plumb bobs, and knew how to compensate. Their expertise allowed multiple teams to work in parallel without compromising the overall alignment. Religious and administrative structures reinforced this technical culture. Priests, scribes, and officials maintained cubit standards, recording adjustments, and ensuring that measurement instruments remained true. The preservation of standard rods and weights was both a spiritual and practical concern. Accuracy was a duty, not a suggestion. The very act of calibration may have been ritualized, blending the sacred with the technical, instilling discipline and communal accountability. This human infrastructure, apprentices, craftsmen, overseers, scribes, was the system that made precision possible. Tools alone cannot produce a straight line or a level plane. Only skill, training, and repeated verification can convert measure into structure. The rods, plumb bobs, and ropes were extensions of the human mind and hand, not replacements for them. The mathematics of the pyramid existed in practice, not on paper. It was enacted, embodied, and observed. Consider the complexity of coordination. Tens of thousands of laborers were involved over decades. They moved limestone blocks, set courses, carved internal chambers. Without a shared standard, without rigorous oversight, errors would accumulate. Yet each stone fits precisely, the base is leveled, the faces rise symmetrically. This outcome is not the product of chance. It is the result of human systems designed to manage error, enforce consistency, and translate abstract measurement into concrete reality. The training of these workers was likely iterative. Early projects may have provided lessons in alignment, leveling, and slope. Master builders would develop methods, refine them, and transmit them. Over generations, these techniques became institutionalized, a body of practical knowledge that could reliably produce monumental structures without relying on sophisticated instruments. Experience replaced theory, observation replaced formal calculation, repetition replaced experimentation. It is important to emphasize the human ingenuity in this process. Modern observers often assume that without lasers or optical theodolites, ancient builders could only achieve approximate results. Yet the pyramid demonstrates that skilled humans, applying disciplined systems of measure, oversight, and verification, can exceed expectations. The cubit rods, the rope-stretched baselines,
the sighting along plumb lines. These were tools in the hands of highly trained practitioners, capable of producing tolerances that challenge assumptions about technological limits. Moreover, the intellectual framework extended beyond the technical. Craftsmen were embedded in a culture that valued precision, permanence, and symbolic meaning. Construction was a social and spiritual act. Accuracy was not optional, it was tied to duty, ritual, and reputation. Measurement became a language for expressing control over both material and space, for creating forms that endure physically and culturally. The human mind, in this context, is the central instrument, and yet questions remain. How did this knowledge first develop? How did early architects discover the rules of proportionality, the importance of alignment, the necessity of repeated verification? Was it trial and error, careful observation of earlier monuments, or transmission from earlier generations of builders? Likely it was all three, a blend of empirical observation, cumulative learning, and institutional preservation. In a world without printed manuals or formal mathematical notation, expertise resided in people. It was their hands, their eyes, their memory, and their judgment that maintained consistency. The system was social, procedural, and hierarchical. Measurement was enacted collectively, verified repeatedly, and enforced culturally. Without these human agents, the cubits and ropes alone would have produced nothing more than approximate forms. And here lies the subtle tension. The physical evidence, the leveled base, the consistent courses, the aligned faces, is measurable and precise. But the mechanisms that produced it were human, experiential, and procedural, not theoretical. Knowledge existed in practice, codified not in writing but in action. As we step back to consider the broader implications, we are faced with a compelling question. What intellectual framework allowed humans to achieve such extraordinary precision with such simple tools? Was it merely disciplined repetition, or did they possess a deeper understanding of proportion, error control, and systemic coordination? How did this expertise persist across decades, generations, and large-scale projects? The answer is not fully visible. But what is clear is this: the Great Pyramid and other monumental structures of the ancient world were not miracles of unseen technology. They were the outcome of human intellect, applied rigorously, preserved institutionally, and practiced collectively. The rods and ropes were extensions of that intellect, translating abstract measurement into enduring reality. And as we prepare to examine the final threads of this narrative, the question lingers: what underlying principles, cognitive, procedural, and cultural, made such feats possible, and how can we begin to reconstruct the full intellectual framework behind one of history's most enduring achievements? Across deserts, river valleys, and distant highlands, a common thread emerges. Structures that rise from the earth, pyramids, ziggurats, grid-planned cities, ceremonial platforms, share more than scale or purpose. They share measurable patterns, standardized units, proportional layouts, leveled baselines, and repeatable construction methods. When analyzed carefully, the evidence reveals not isolated brilliance, but a coherent approach to engineering grounded in human ingenuity, empirical measurement, and disciplined process. The Great Pyramid stands at the center of this pattern. Its base, squared to within centimeters, its faces rising in uniform slope, its orientation aligned almost perfectly to the cardinal points, demonstrates a level of precision that surpasses what conventional assessments of Old Kingdom tools would predict. Yet it was achieved without modern instruments. Repeated use of cubits, verification through sighting and leveling, and careful oversight collectively allowed human teams to translate abstract measurement into monumental reality. Comparative analysis strengthens this perspective. Mesopotamian cubit rods, Indus Valley rulers, and distant settlement layouts reveal recurring measurement systems and proportional strategies. While each civilization adapted to its environment and materials, the similarities suggest shared principles, whether transmitted through contact or arising from universal constraints on human scale, labor, and materials. These patterns are measurable, consistent, and repeatable. They are the empirical fingerprints of disciplined engineering. This shifts our understanding of ancient capability. The narrative of primitive technology yielding approximate results is incomplete. Ancient builders, operating within simple tools and natural materials, developed systems that controlled error, standardized measurement, and coordinated labor across decades. Their knowledge was practical, procedural, and human-centered, yet it allowed outcomes that rival modern expectations for accuracy and scale. Measurement, oversight, proportionality, and apprenticeship formed an integrated framework that produced monumental precision. The evidence invites a profound reconsideration of engineering history. Rather than viewing ancient structures as the product of rudimentary tools or inspired improvisation, we can recognize them as the culmination of systematic, empirical practice. The mastery is human, grounded in observable methods and verifiable data, not myth, speculation, or lost technology. And yet this realization raises a deeper question. If we accept that ancient civilizations could consistently achieve such precision and coordination, using standardized measures and disciplined process, then how should we rewrite the story of technological history? What does it imply about the origins of measurement, quality control, and large-scale project management? If the ancients mastered these principles empirically long before industrialization or formal engineering theory, then the timeline of human innovation itself deserves reconsideration, a challenge not to imagination, but to the measurable record that endures in stone, rod, and rope. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.